In this equilibrium problem, we have a lot to work on. We're introduced to the Haber process, which produces ammonia gas from the reaction of N2 and H2. We're told that at 500 degrees Celsius, the equilibrium constant in terms of concentration, Kc, for this reaction is 0.061. We have measured the partial pressures of all of our reactants and our product in a reaction vessel at 500 degrees Celsius as 1 atmosphere for ammonia, 0.5 atmospheres for hydrogen, and 0.5 atmospheres for nitrogen. We're asked if this reaction is currently at equilibrium, and if it's not, we would like to know which direction the reaction will proceed to establish equilibrium. So we've got to do a few things. We need to understand that we're taking a snapshot of our reaction according to the data shown in the table here. Therefore, this requires us to determine a reaction quotient Q. From this information, we can calculate the reaction quotient, a snapshot in time of where our reaction is right now. We also need to understand that the partial pressures that are listed in this table will allow us to calculate Q in terms of partial pressure. We can't compare Q in terms of partial pressure to an equilibrium constant in terms of concentration directly. Instead, we'll need to come up with a way to convert the equilibrium constant in terms of concentration to one in terms of partial pressure. So let's do that first. For this reaction, we could write down an equilibrium constant expression in terms of concentration, Kc, as the concentration of our product, ammonia, raised to its stoichiometric coefficient for power, divided by the concentration of hydrogen, raised to its stoichiometric coefficient, multiplied by the concentration of nitrogen, raised to just 1, its stoichiometric coefficient. Similarly, if we wanted to, we could hypothetically think about an equilibrium constant expression in terms of pressure. Our equilibrium constant in terms of partial pressures is given as the partial pressure of ammonia squared, divided by the partial pressure of hydrogen cubed, multiplied by the partial pressure of nitrogen, raised to the first power. What do we know about the relationship between pressure and concentration? Well, nothing directly, but we do have an ideal gas law, PV equals nRT. And in this ideal gas law, we do have a number of moles given and a liter volume given, and we know that molarity is moles per liter. So if we rearranged our ideal gas law, dividing both sides by volume, we'd end up with this expression. This whole thing is just molarity. So I've replaced that here. We could think about this molarity as molarity of any substance. It could be the molarity of ammonia or of hydrogen or of nitrogen. In fact, anywhere we see pressure in an expression like here, 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 we could substitute in the molarity of the substance multiplied by R and T. So let's do that over here under Kp. Our Kp expression becomes the concentration of ammonia multiplied by RT and square that whole quantity. The partial pressure of hydrogen becomes the concentration of hydrogen multiplied by RT and cube that quantity. For nitrogen, we take the concentration of nitrogen multiplied by RT. And we could simplify this down a little bit further. We could say that Kp is equal to the concentration of ammonia squared times RT squared over the concentration of H2 cubed times N2's concentration multiplied by RT to the third power multiplied by RT again, now to the first power. And what we would recognize from this is that this whole thing right here is exactly the same as this whole thing up above in our expression for Kc. Kp, therefore, can be given in terms of Kc. Kp is equal to Kc multiplied by RT squared over, in this case, it's RT to the fourth, and I'll put parentheses around each of those. This squared power came from the number of moles of all of our gases in our products up in the reaction above. This fourth power came from the combined numbers of moles of all of the gases in the reactants in the reaction above. So we could simplify this even further and say that Kp is equal to Kc multiplied by RT raised to the delta N power, where delta N is number of moles of product gas minus number of moles of reactant gas. In this case, it's -2. So let's use this new expression to solve for Kp, given what we know about Kc for this reaction. We were told up above that Kc for this reaction is 0.061 at a temperature of 500 degrees Celsius. Remember that for gas laws, temperatures always have to be in Kelvin, so I'm going to immediately add 273 to this to convert Celsius to Kelvin. If I want Kp, I can plug in this information. Kp is equal to Kc, 0.061, multiplied by R, our ideal gas constant, 0.08206 when we're dealing with pressure in atmospheres, times our Kelvin temperature, 773, all raised to the -2 power. Moles of product gas minus moles of reactant gas. 2 minus 4. Plug this into a calculator, and our equilibrium constant in terms of pressure ends up as 1.5 times 10 to the -5. Alright, so I reset the board, and what we now know is that our equilibrium constant in terms of pressure is 1.5 times 10 to the -5. We can use the information in the data table down here to calculate at a snapshot in time whether our reaction is at equilibrium. To do so, we determine a reaction quotient. We determine a reaction quotient in exactly the same way that we determine an equilibrium constant expression, the difference being that an equilibrium constant is always representative of equilibrium, while a reaction quotient is just a snapshot of a reaction at some point in time. So we'll use these data to just plug into our reaction quotient. Our reaction quotient is the partial pressure of ammonia squared divided by the partial pressure of hydrogen cubed and the partial pressure of nitrogen. In this case, our reaction quotient calculates as 16, and what we want to do from here is compare that reaction quotient, our snapshot of our reaction, to our known equilibrium constant, the value that this reaction will take on when it has established equilibrium. What we find is that because 16 is larger than our known equilibrium constant, Q is greater than K. What does this tell us? Well, our snapshot, Q, gave us information about the ratio of quantity of products over quantity of reactants. Effectively, Q is telling us about what the ratio of products to reactants is right now. This is large compared to what it should be if we're at equilibrium. In other words, there are right now too many products in this state of our reaction. If there are too many products, then our reaction is going to proceed in such a way that it consumes some of them. It's going to revert back to reactants. So our reaction proceeds to the left.